you ever imagined how your life would be without the sense of touch? Every day, we interact intensively with machines through auditory and visual senses, but still, we often ignore the sense of touch that we trust most. Unlike acoustic and vision information, haptic information is bilateral, adhering to the law of action and reaction. Haptic studies often consider conventional spring damper model-based approaches and force sensors, despite their limitations. So, we developed an AI-based approach for vivid force sensation reproduction through a virtual model that replicates the actual environment. We considered a disturbance observer, DOB, and a reaction force observer, RFOB, based sensorless force control mechanism. This procedure involved 3 stages: abstraction, reconstruction, and reproduction. In the abstraction stage, data on motion with the object responses were recorded for different ramp force commands. The reconstruction phase involves feature extraction and selection and model building. A feature is defined using a mathematical notation as a 3-dimensional entity with a feature number, cycle number, and elapsed time. 9 features were considered as an instance of the feature matrix without solely relying on motion parameters as the main determinants of force feedback. We analyzed the nonlinear haptic data using Spearman's correlation and identified 6 crucial features, namely compression depth, velocity, acceleration, instantaneous stiffness, instantaneous viscosity, and previous force response over acceleration. These features are considered as significant features to be used as inputs to the AI model. Several object reconstruction methods were analyzed, including the model-based approaches with constant and polynomial approximations for stiffness and viscosity. It seems that complex mathematical representation demonstrates a higher R-squared score and lower the regression losses, namely mean absolute error, MAE, mean squared error, MSE, and root mean squared error, RMSE. But it is still incapable of accurately modeling the object's behavior, as the actual response data points did not align with the red surface generated by the polynomial relationship using the MATLAB curve fitting tool. AI algorithms considered include linear regression, support vector regression, random forest regressor, deep neural network, and LSTM recurrent neural network. Data with different ramp rates were used as the training and test datasets. The predicted force response generated by each AI algorithm was compared with the actual force response, which is represented in blue. It seems that the results of the random forest algorithm demonstrated a closer alignment with the actual force responses compared to the other algorithms. This is particularly noticeable when comparing the force response versus time and the force response versus compression depth and time graphs for all 5 algorithms. Regression metrics were utilized to evaluate the results, and these results confirm the findings from visually examining the graphs of all algorithms. The random forest algorithm exhibited lower regression losses, including MAE, MSE, and RMSE, compared to the other algorithms. Also, it has achieved the highest R-squared score. Therefore, the random forest algorithm was chosen as the most suitable AI algorithm for haptic object reconstruction, leading to its implementation in the haptic object reproduction phase. The results reveal that when using the random forest model, compression depth is the most crucial feature by importance for building the AI model. To validate our approach, a comparison of force responses was conducted using the same position reference input. It appears that the force response predicted by the AI model closely aligns with the real force response, whereas the spring damper model exhibited a greater deviation from the actual response. During the reproduction phase, the force sensation is replicated using an AI model in conjunction with the hardware to virtually simulate the experience of interacting with a tangible, deformable environment in the absence of a physical object. The selected AI algorithm transformed it into an intermediate format for deployment, with the hardware facilitating real-time haptic object reproduction. We used predictive model markup language, PMML, to migrate the Python or our developed AI model to hardware-supported C or C++ language. Our study introduced a promising AI-driven approach for reproducing vivid force sensations by utilizing a virtual object model that accurately simulates the real object using haptic information obtained through a sensorless force control mechanism, enabling the users to perceive the force response as if they are interacting with a real environment in the absence of a physical object.